Welcome to C++ exceptions and stack unwinding. It's early in the morning, so forgive me if I'm a little slow. My name is Dave Watson. I am a Facebook engineer here to talk to you about exceptions. So while I'm going to teach you a little bit about how Facebook uses exceptions in stack unwinding, I'm also the current libunwind maintainer, so most of my talk is actually coming more from a maintainer standpoint than from as a Facebook employee. At Facebook, though, we do use Linux 64-bit x86. That's what I'm most familiar with. We're going to be talking about a handful of different stack unwinders. They're listed up here on the slide. These are all kind of the ones that are most used in Unix operating systems. So if you're using Windows, I don't nearly have as much knowledge about that. Windows uses SEH, structured exception handling, which is a little bit different, but actually you'll probably learn quite a bit in this talk anyways. They're similar enough to still be relevant. So of the unwinders that are used in the Unix-based operating systems, we have libgcc. You guys are probably familiar with GCC. It has a stack unwinder in libgcc used for exceptions and backtrace functionality. The one that I'm the maintainer of, libunwind, started as an HP project for the Itanium architecture. Libunwind actually provides its own interface to programmatically unwind the stack. So you can unwind and see things about the frame, the current function name, look at some of the registers, do introspection, not just while unwinding for exceptions or backtraces, but really whatever you want to use it for. There's another project. Confusingly, it has the exact same name. It's also called libunwind. It's part of the LLVM group of projects. The GitHubs are up there on the slide. They're unfortunately very similar, so grab one or the other. LLVM's libunwind uses the same interface as libunwind, so I'm going to talk about the libunwind interface that's implemented by those two projects, but is not the same as libgcc, which doesn't export a public unwinding interface other than throwing exceptions. Cool. So we're going to talk about a little review of zero-cost exceptions. You guys are probably pretty familiar with it, but we'll do some review for 5 or 10 minutes and make sure we're all on the same page. We're going to then talk about the various layers of abstraction that we have to get through to actually get from throwing an exception to handling it in a catch statement. So this includes the C++ API and ABI, the Itanium ABI, and finally the libunwind API and ABI. Then we're going to dive into some things that are pretty operating system specific, so dwarf, elf, and what syscalls actually have to be available to do unwinding of exceptions. So I mentioned Itanium. Itanium is an architecture, was an architecture. People still use it. We mostly care about, when I say Itanium in this talk, the exception handling ABI. It has outlived the architecture and become widely used for all the different Unix operating systems. So when I say Itanium, don't think architecture, think, oh, exception specification. This is what everyone is using to unwind their exceptions. Cool, so zero-cost exceptions. Hopefully this means if we don't use exceptions, or even more specific, don't throw an exception, we're not actually paying any cost for having this exception handling in the code. And let's see if that's really the case. So we're going to compare it to return codes. Here's a super simple example of some function that calls another function using return codes. So bar returns a return code. In this case, we're going to check and see if it is less than 0. If so, we're going to assume that's an error and propagate it up the stack. If not, we'll go do some real work and return a different return code. We generate the assembly for that. This is x86 64 assembly. I'll just walk you through all the examples of assembly. In this case, we do a little stack adjustment. We actually call the function. We do some tests. If the return code is less than 0, we do something different. We adjust the stack again and return. Great, pretty straightforward. 7 or 8 different instructions. The comparison, the try-catch. We're assuming in this case that bar throws an exception and we want to handle it somehow. I didn't actually put anything in the block, but you would do something there, catching all exceptions in this case. Generate the assembly, great, zero cost. All that introspection of what the actual return code was has disappeared. And it didn't disappear entirely, it actually went somewhere else. We just generated it into a different block of code. So the zero cost just generates the two pieces of code, the handling of the error or exceptional case, into a different block so we can have a hot piece of code and a cold piece of code. And we can actually see our first little bit of the C++ exception handling ABI here. CXA begin catch and end catch. Of course, had I put something in the catch statement, there would be code generated in the middle to actually implement the catch statement. So in addition to splitting apart the exception handling in the actual instructions that you want to run, we actually need a little bit more information. I can't put it on a slide because unfortunately I don't know of any great tool that will put a human readable version of it, but it's super easy to explain. If you have multiple catch statements, you can have different exception types that you want to handle. So we actually generate a little table that says, oh, here's the types of the various exceptions that we're going to handle, and here is the catch statements for them. So it'll jump to the little piece of code called the landing pad for that catch block. In addition, it generates a little stub to actually clean up the frame. So say we threw an exception from bar and didn't want to handle it. We didn't have that last catch block that was catching all. If we just wanted to propagate the exception up the stack, we'd actually want to delete everything that had a destructor on the stack. So in this case, I stuck up just an example, a mutex that probably wants to get unlocked using that lock guard. So it'll generate a little stub of code that will run all the destructors and then continue unwinding up the stack. So the return code equivalent of throwing is just returning return code. It's a single instruction. Conversely, the zero cost exceptions have eliminated most of the cost from catching exceptions and instead put all the complexity into throw. So a super simple throw statement gets generated into something like this instead. So we call CXA allocate exception. We initialize the exception with a bunch of instructions there, and then we throw the exception. Great, so that's the end of our little bit of review. Let's start looking at what these actual C++ ABI functions, how we would implement them and what they actually do. So the first ones we saw were begin catch and end catch, bookended on top of our catch statements. So exceptions in C++ are reference counted, so you can do things like get the current exception or exception pointer. So the actual exception object isn't deleted until the reference count goes down to 0. In C++, you're also allowed to have a stack of exceptions. So if you are in a catch statement and you want to throw another exception while you're already handling an exception, yeah, sure, you can do that. Go ahead. We'll just keep track of it in a stack. At Facebook, we actually have some tools that will introspect the stack and print all the exceptions that you're currently handling at the same time. I'm not going to recommend this as a great way to deal with exceptions. You probably don't want to handle more than one at a time, but it's totally supported. So these functions are super easy to implement. They're very short. Next, we have allocate exception. The implementation under the hood is pretty much as it says on the tin. It allocates an exception. It pretty much just calls malloc. So it has a little piece of memory there and sticks the exception into it. For return codes, these are passed in register or on the stack, back up the stack as we're unwinding. For exceptions, well, they may be a little bit bigger, so we generally put them on the heap as we're unwinding the stack, because the stack is going to disappear on us as we're throwing the exception. So one little trick here is that what if we are actually throwing bad alloc? So when we say we're using our system allocator, it runs out of memory somehow and says, okay, I'm going to throw bad alloc. But the first thing you get to in the C++ ABI is, oh, allocate exception, which is just going to call malloc using the system allocator. Well, it's probably going to say, I don't even have room for you to allocate bad alloc. As it turns out, we just allocate a little bit of memory at startup and then stick bad alloc into it. So we kind of just like work around it. So we have just enough memory for a few bad allocs to get thrown up the stack. So pretty much the rest of the talk is talking about how CXA throw is implemented. So how do we get from the throw to the landing pad? This is pretty much all the complication of how exceptions are implemented. So that's it. That's all the C++ I'm going to talk about. We're now diving into the world of the Itanium ABI. The Itanium ABI is language agnostic. So it implements exceptions for a bunch of different languages. So I may mention a few of them, but this isn't C++ specific at all. CXA throw is actually implemented very simply. It does a tiny bit of accounting for the reference counting of the exception, and then dives right into unwind, raise exception. So we pretty much immediately jump into the Itanium ABI. So the Itanium ABI, as an unwinder, is implemented in libgcc or the other unwind libraries I listed. The personality routine, which is the language-specific part of the unwinding, is implemented in your C++ library. So The one we use is libstd C++, and that's where the personality routine lives, in this case called GXX personality v0. And so many years ago, before I knew as much about exception unwinding, I knew this as the thing that was the first thing to complain when you tried to link your C++ library together and forgot to link with libstd C++. Always complains it was missing. Great, so your personality routine, what it's actually doing is walking that table that lists, oh, here's your catch blocks with the type of exception we wish to handle, and here is the actual exception you're throwing. And it just tries to match up the types. So it walks the table, finds the right landing pad, catch block to go to, and jumps there. It's actually pretty simple. It's implemented in 2 or 3 pages of code. It also has a different mode where it will say, I don't know how to handle this exception, so we're going to keep unwinding the stack farther and run the little stubs that run the destructors for this frame. That's all it does. It may need a little bit of extra information to do this, so we have unwind get and set instruction pointer to find out where we are, or to set it to the correct landing pad. We also have access to all the general purpose registers on the machine. These are all abstracted out in the Itanium ABI. They're just numbered 1 to 16 or however many you actually have. So generally the Itanium ABI is implemented in terms of a lower level API. In this case, libunwind has its own API, and it's pretty straightforward to implement the Itanium ABI in terms of libunwind. So this is what libunwind or LLVM's libunwind provides you. You have an initialization function, unwind init local. So we are initializing our unwinder from this place right here where I am on the stack right now. And so we are going to unwind from here, wherever you call this function from. There is an init remote variant as well. So you can initialize from somewhere else, from a different process, from a different machine, from a core dump. So all sorts of cool things you can do from where you want to start unwinding. Unwind step is where most of the magic happens. It is what takes you from your current frame to the previous frame. Unwind resume actually resumes execution from wherever you are. So you call unwind step a few times, and then you can resume from a few frames above as if you had called return instead. We also have get register and set register that implement the get and set for the Itanium ABI. And also get proc info. This is the thing that, generalizing a little bit, that gets enough information so that the personality routine can go and handle and knows all the types of the different catch blocks. So let's go ahead and try and implement a super simple exception handler. This code is actually just simplified right from the code that libunwind actually does to implement exceptions, so it's actually exactly what is used. Itanium ABI specifies a 2-phase unwinding process. The first phase is the search phase. We're going to search through and try and find the correct handler. So first, we just initialize from wherever we are, enter a while loop to unwind frames until we find the right handler. The first thing we do is step backwards. The unwind step returns either an error code, or it tells you it has gotten to the top of the stack and there's nothing more to unwind. Or it says, okay, great, we unwound 1 frame successfully. But the first thing we do is actually just step back 1 frame. Why would we step back 1 frame right away? Well, it's because we're actually in the Itanium ABI, we're actually in the unwind raise exception function, and we are guaranteed to not have your catch handler in the unwind raise exception function. So we step once to get back into your function. So the first step is good. We're just getting back to your function. We grab whatever information the personality routine may or may not need, and we call it. Personality routine takes an enum. In the first phase, it is search. So it searches through its tables to see if there is a match for the currently thrown exception. The current exception is in the context object. So this is abstracted out. C++ knows what's about the context in the personality. The language agnostic Itanium ABI knows nothing about it. It knows nothing about exception types. So the personality routine takes care of deciding, hey, is there a catch statement here or not? If there is, it says handler found. We break and go to phase 2. If there's not, eventually unwind step will return, oh, we got to the top of the stack, and terminate is called. So let's say we found our handler. We're now going to start the second phase of the unwinding. We restart from the beginning. Initialize back from the very beginning, unwind init local. Next, we step, again right away, step, grab the personality routine. This time call it with the cleanup enum. So this time it's running all your destructors. It also returns, hey, is this the right location that we actually need to install the context or not? So if this is our handler. We're not going to clean up. Instead, we're going to reset the instruction pointer, which is done somewhere in the personality using unwind set instruction pointer, to the correct catch block. And then libunwind says unwind resume. So it resets all the registers to the correct values and resumes execution from there. Great, so we have this two-phase unwinding process specified by the Itanium ABI. What does this actually buy us in practice? As it turns out, not a lot. It lets you have the full stack trace available to terminate if you threw an exception and it was unhandled. So you as the programmer, your value in two-phase unwinding is just getting better debug info. You can actually write the unwinder with the single phase of unwind if you wanted, and it would be faster. Cool, so terminate, if we do get terminate, let's see how this actually works in practice. So here's a simple example. I'm using GCC to compile this code. So I made main. To make it a little more complicated, I said std thread, let's just throw an exception from the std thread, in this case bar. So if everything is working as I said it would in the previous slides, we should have the full backtrace available to us in the debugger. It should say, oh, bar through an unhandled exception, and then we should see whatever started thread. So here's what I got. I did this on Linux. I think I used GCC 6 for this. So here's my backtrace. It definitely threw the exception, definitely called terminate, but I don't actually see bar in here anyway. There's std terminate, and then there's start thread. As it turns out, GCC has a bug in it, or an issue. Before GCC 8, which is not out yet, I believe it is fixed in trunk, but not in any released compiler. What actually happens is this std thread, before it calls your user function or your lambda, it actually has a try-catch around it. So it catches all. It catches all exceptions. So we're switching from phase 1 to phase 2. It needs to do this to implement pthread cancel. So I actually don't use pthread cancel. I don't care about pthread cancel. Neither does the code. It rethrows the exception. And that's fine, but that means we've gone through phase 1 and phase 2, found the handler, restarted execution. Rethrow exception is now going back to phase 1. It actually calls terminate because it didn't find a handler for it. Unfortunately, we're at the wrong location and our debug info is all screwed up. We can fix this though. We stick a no except in there. What does no except do? So this is straight from the standard wording. No except may or may not unwind the stack, which potentially allows the compiler to implement no except with, well, implement it faster. Well, in practice, ignoring the standard text, but what actually happens, let's stick the no except in there and run our code again. It actually looks much different this time. Instead of 7 frames, we now have 16 frames, which is great. So what actually happened was the personality routine realized there was a no except in there, and there probably shouldn't be any exceptions being thrown. Instead, we immediately call terminate. So I really like this example because we can actually see all the different layers of abstraction at work here. We can actually see bar in the backtrace. We see CXA throw, the C++ ABI. We see unwind raise exception, the Itanium ABI. We then see the personality routine being called and finally terminate. So it's all just kind of laid out for there for you to see. So in addition to throwing exceptions, or even pragmatically unwinding your stack, there's a couple other really commonly used functions that use the same machinery. So POSIX provides setJump and LongJump. And C, these are actually easy to implement. SetJump just grabbed all your registers, including your instruction and stack pointers. And LongJump, after you had presumably increased your stack size, done a couple functions, it's just a non-local return. It wants to return not from the current function, but all the way back to where setJump was called. So the way it does this is just slams back in all the registers it saved, including the stack pointer and instruction pointer. Works great in C. It doesn't work so great in C++ because we need to run the destructors. So instead, we use the same machinery. Instead of calling a personality routine to try and decide if we have a catch statement and trying to match up exception types, we do it instead by just saying unwind to this instruction pointer in this location. So the actual Itanium ABI function is called unwind, force unwind, I believe. So it's just a different place to stop the unwinding process. Similarly, the GNU C library provides backtrace. Super useful. We use it all the time. You pass it an array, and it fills it in with all the instruction pointers up the stack. So a whole array of instruction pointers representing your backtrace. And this is implemented the same way. It unwinds the stack one frame at a time, fills in the instruction pointer. It only uses like a phase one kind of unwind though. It's not actually calling any destructors, not calling any personality routine, not calling any stop function like set jump and long jump. It just goes all the way back up into the stack until it says either I filled in the entire array that the user passed me, or there is no more stack to fill in. Cool, so how do we actually implement unwind step? That's probably the most complicated process of all this. Like how do we get from one function to the previous function? Dwarf debugging symbols are really how we do this. So the ELF is just a file format. We don't actually care about it in terms of this talk, except that there is a section. One of the pieces of the ELF format is an EH frame section, an exception handler frame. So it gives us enough information in dwarf format to actually go and unwind the stack. So there's some command line tools. You can dump your dwarf expressions from your file. Use readelf, debug dump frames, and give it the binary name. It'll spit out some stuff like this for every single function. So it's actually a lot of data. So they're called dwarf, DWs for dwarf, CFA is for canonical frame address. So canonical frame address, if you're on an architecture and you're using frame pointers, it is this frame pointer. It is just saying this is what the frame pointer is. Of course, using dwarf unwind information, you don't actually have to have a frame pointer, so you can compile without frame pointers, or maybe your architecture doesn't use them, and dwarf will still work just fine. So I'll just tell you, explain how some of these work. Advanced location is super easy. It just means advance one location in your instruction stream. So in this case, the first one is advance 1. The def CFA, there's 3 of them up here, def CFA offset, def CFA register, def CFA. These are defining what your frame pointer is, your canonical frame address. So normally you specify both the offset and register. You can also specify either just the offset or just the register and keep the other half of it the same. So the first one we're saying reset the offset to 16 but keep whatever it was before for the register. The second one is saying, our new CFA register is RBP, the frame pointer on x86 64, but keep the offset as 16. And the last one says RSP is the new frame pointer with offset 8. And this corresponds to the generated assembly like this. It's a standard function prologue of pushing the old frame pointer onto the stack, moving the current stack pointer into the frame pointer, doing whatever we did in our function, and then the standard function epilogue of popping off the old frame pointer. So visually, that looks something like this. We're stack. I'm just assuming like in this diagram that we're pushing things onto the stack always, never popping them off. We have a series of registers that we want to know how to restore, how to get from this frame to the previous frame. So presumably there's some registers that were saved that we need to then put back into the registers from the stack before the stack disappears. Because as you're unwinding the stack, you need to grab any information you need out of the stack before you move to the previous frame. So in this example, it had pushed R1 on and then pushed R6 and then pushed R1 on again because it had done something with it. It also has some frame-oriented registers on there, like the return address and the frame pointer. So we need to restore the registers when we're unwinding, but what registers do we actually need to restore? It turns out not all of them. We can kind of break up the registers into several different categories. The caller saved, the callee saved, and the frame related, so the instruction pointer, frame pointer, stack pointer. So as it turns out, the only ones we need to save are obviously the frame related. We want to know where our canonical frame address is, our frame pointer. But only the callee saved registers need to be saved. For the caller saved registers, your function, if it has a catch statement in it, it actually knows exactly what it needs if it's going to resume execution there. So when it generates the code to call a function and has a little landing pad, the catch statement, it knows it can insert some code into the landing pad to go and grab these registers again and restore them if it needs to. It can't do the same for the callee saved registers. It doesn't actually know which registers were used. It doesn't know where they were stored. So instead, the dwarf information has enough information to do that to restore just the callee saved registers. Cool, so we're going to take a little aside into one of the bugs I had to solve in stack unwinding. So about a year and a half ago, I spent most of my time working on JMalloc, which is our memory allocator implementation. It has a debug mode where it takes stack traces every X bytes that you allocate. So you allocate every 100 bytes, it will go and take a stack trace when you call malloc. So it can try and figure out, give you a nice profile of which pieces of memory are allocated and where they're allocated from. As it turns out, one day, one of our engineers said, hey, this is taking 3 times longer to run our program than normal, and I've narrowed it down to this unwind information. Like, grabbing this backtrace is taking way longer than it used to, and we have no idea why. And I was like, well, we haven't really changed JMalloc recently. Let's take a look. Let's debug this and figure out what's going on. And after about 2 weeks of banging my head on this problem, I came up with this small, reproducible test case, this 3 lines of code. So, clearly, if you were to compile this with an optimizing compiler, 03 or 02, this would just be nothing. It would just return right away. I mean, it's a char array of size 1, and it's aligned to 32 bytes. Okay, great. Even if you were using a non-optimized mode, you'd think this would compile down to something that would maybe allocate space for this on the stack with a prologue and epilogue, and then return. As it turns out, it does that, but in the most convoluted way possible. First, it takes not the return address, but a pointer to the return address, and stores it in R10. Then it aligns the stack using a mask. So the stack goes down. It says, let's AND out the 32 on the bottom, and so we'll align it to 32 bytes. Then we push the address to the return address onto the stack. Then we're going to do a standard function prologue, push RBP, and then move in the current stack pointer to the frame pointer. Then it decides to push and pop R10 for whatever reason, and then finally it does a standard function epilogue of popping the frame pointer, and then again it takes the address of something and stores it in the stack pointer. So kind of crazy. The dwarf it generates looks something like this, which is also crazy. So both the assembly generated and the dwarf expressions are correct. They both run just fine. They are just non-standard code that would be generated. So while 95% of functions probably just use advanced location and def-CFA and maybe define a few where the registers are saved, you can also define expressions in dwarf. So dwarf actually, as it turns out, is completely Turing complete with the expressions. It provides a full interpreter stack machine that you can use to specify whatever you want. So this, take the address of something and dereference it, is not, you can't specify this in normal dwarf, only in expressions. So the one we care about here is the second one, def-CFA expression. It takes the frame pointer register, RBP, subtracts 8 from it, dereferences it. Okay, great. It's actually pretty short in the dwarf, but it is not something that is standardly done, so it was making our whole program go slower. To understand why it was going slower, I'm going to have to get through how the rest of the unwinder works. But expressions can be totally arbitrarily complicated. This one is not made up. I grabbed this from the standard library. It grabs a couple registers, puts some literals on the stack, ANDs them together, does greater than, shift left, but totally, completely arbitrarily complicated. As it turns out, there's a researcher wrote a whole paper on how to maliciously attack your program using dwarf instructions. That's kind of cool. I thought it was a good read. Cool, and now we're really coming to the heart of the winder, or what I consider the heart. How do you find these dwarf instructions? Actually, implementing a dwarf parser is great. There's a bunch of them out there. It is not that interesting. As it turns out, all the different unwinders all parse it the same. I mean, they'd have to be correct. But how do you find the actual dwarf info, and how do you make it go fast? As it turns out, at least in the teaser for the talk in the slide, there's a giant lock in how you find the dwarf information. So if you had statically linked your binary all together in one giant blob, great. There's just one EH frame section. That's the only one you have to search. It's super easy. If you had dynamically linked things together, there's a bunch of different sections that you now have to go and try and read and find the right one. So some of this is operating system specific. You can, of course, go read the proc file system in Linux and try and figure it out. glibc provides deal, iterate, phtr. So iterate the dynamically loaded libraries and find the headers. You can also load dynamic libraries, DL open and DL close. So the lock we're taking is the list of dynamically loaded libraries. So while you're iterating over things, you can't open and close libraries and vice versa. So if you're complaining about exception speed in multi-threading, this is probably the issue you're running into first, is that there's a hard to rewind where there is a giant lock that you try and have to get around. And how we get around this is completely different for the different unwinders. They all basically use caching in some form or another to try and cache this information so they don't have to iterate over all your loaded libraries. So the main problem with unwinding is deal open and deal close. So great, you open something. You can't actually unwind unless it's already open. So presumably you already have the code loaded if you're throwing an exception on unwinding. Let's assume you have already done deal close in a safe manner and you're not trying to unwind through a closed library, which again, that's correctness on your part. The problem really comes down to we're now deal opening something after having deal closed something. It doesn't have to be the same thing, it can be completely different. These things can be put in the same place in memory. So when we're talking about caching, we have to make sure our caching is correct, even though things may be changing using deal open and deal close at the same time. So the different caching strategies are something like this. libgcc is the most conservative. It always takes this lock. It always calls deal iterate phdr, grabs the lock. Deal iterate phdr actually has a super interesting optimization in it. It has a count of how many times you've called deal open and deal close. If that count is the same, we just assume that our cache is correct. So nothing was loaded, nothing was closed, we can use the cache. Immediately goes and checks the cache. Its cache is pretty small. It caches 8 objects. The things it caches are, it is caching an instruction pointer range to the EH frame section in your object file. If it's not on the cache, it has to walk the whole list of all the object files and try and find it. LLVM's unwinder, LLVM libunwind, has a different strategy. It also does caching. It has an unlimited cache. As far as I can tell, it's just a linked list. It uses a read-write lock to protect it. So if it's not updating the cache, all the readers can just use the read lock and try and read the cache. It also briefly takes the global lock always to make sure that the cache is valid. But then it can grab an unlimited number of things from it. It doesn't cache full object files, it caches the functions. So each function has a series of dwarf instructions associated with it. So a slightly smaller range of IP addresses, or instruction pointer addresses, to the functions that it's actually using for the dwarf instructions. libunwind takes a different approach from both of those. It's an even higher level cache. It also doesn't always take the global lock. It is a little more optimistic. It says, hey, if you're just trying to get information out of this, you're just doing a backtrace, you're not actually resuming execution, we're just not going to take the lock. We're going to assume our cache is correct. It does have a few checks to try and see if the cache is correct, but there could always be a race with the actual deal open and deal close. But most programs don't use deal open and deal close, so not usually an issue. When it unwinds an exception, it does always take the lock so that your code never crashes. It's always correct with deal open and deal close. So the caching that libunwind does is quite a bit different. It looks more like this. Instead of a range of instruction pointer addresses, we're caching only a single instruction pointer address ever. So you have to have this individual instruction pointer have been through this point before, have thrown an exception through this exact point before for it to be in cache. But that means we can cache things much faster. So I said that each function call, or each place you're throwing an exception, you have to restore a specific list of registers, the call save registers. So how do we restore this particular list of registers? Well, we can run through all the dwarf instructions and figure out the last place that each of those registers was modified, and then we know how to restore it. So the dwarf tells us how to restore it. But let's say instead, we run through all of it the first time and then just save it for this individual location. So for each of these function calls, in this example of like void foo, multiple things could be changing on the stack for that function. The dwarf instructions specify the entire function, but we don't save the information for the entire function. We only save it for the function calls. So again, our cache is instruction pointer corresponding usually to a function call or a throw statement to a list of call save registers to restore. So libunwind actually doesn't run any dwarf assuming you've hit the cache. No dwarf pricing, nothing. So we're caching the results of running the dwarf instead of caching the dwarf to run. It is much more sensitive to hash table size. So if your cache is too small because it stores individual instruction pointers. It's going to take a lot longer to try and go and do the full parsing and try and find the dwarf again if you've missed your cache. So we actually have one other thing that we implement in libunwind. We actually have a backtrace cache as well. So we implement fast backtraces. So backtrace is actually mostly what we use libunwind for at Facebook. None of the other unwinders have fast backtrace support. You can, of course, grab a backtrace by just using your frame pointer, assuming you've compiled the world with frame pointers. And you probably would have to compile the world with frame pointers to guarantee you have them everywhere. And we actually do. All the code that we compile from scratch, we enable frame pointers everywhere. Of course, we have a bunch of code that we didn't compile ourselves that may or may not have frame pointers in it that we would like to still get backtraces for. In addition, I showed you the dwarf expression before. That actually messes up the frame pointer unwinder because the return address is not directly in front of the frame pointer links. It actually uses a non-standard location to store the return address, so frame pointer unwinder broke on that as well. So the backtraces, what do we need when we do a backtrace? Previously Unwinding, we've been talking about all these callee save registers that we need to go and parse the dwarf to do. We don't actually need any of these. We're not restarting execution. The only thing we care about is where was my previous canonical frame address or frame pointer, and where is my return address? Where is the instruction pointer? That's all we're filling in the array for backtrace. That's all the information we need. As it turns out, we can compactly represent all this information in a much tighter format than could be done using the full unwind info. In fact, we compacted down to 64 bits. So dwarf is a little bit more verbose format for that cache. It turns out some architectures actually have more compact representations of their full unwind info. So if your function only needs to restore 0, 1, 2 registers, we can compact that down to a minimum amount of information as well. So if we're using backtrace, fast backtrace support, we try the fast backtrace cache. If we miss there, we try the full unwind cache. If we miss there, then we're going to go and try and search through all the object files and find the correct dwarf to rerun to get us to the correct location. So this fast cache looks something like this. There's various different types of unwinding that fast cache can do. Of course, if you have a frame pointer, it can say, hey, I know this is a frame pointer, let's just use the frame pointer to unwind. Of course, this isn't always RBP. Sometimes, like if you're in the exact wrong location, it could be RSP, as we saw in one of the examples earlier. There's also signal frames, which are slightly different. We can unwind to them as well. We just need to know where the uContext structure is. Again, this is operating system specific, but actually it's the same on FreeBSD and Linux and several others. uContext just has saved all the registers for us before it jumps into the signal handler. So let's go grab the previous set of registers, and we know how to do that. So we store an enum in our packed data there, as well as whatever information we need. So either RBP or RSP for frame pointer, or we know we need to go and grab the uContext, and there's an offset in there. So to fix that issue we were having earlier, for the alignment, stack alignment of 32, I actually just added a new mode to this saying, oh, it's an alignment instruction. Now you need to go grab RBP and dereference it, and that's going to give you your new frame pointer. So if we miss on this cache, of course, we just fall back to normal unwinding. So the bug we were having earlier, like most bugs in production, is actually several different things all had to fail all at the same time. So we had to teach the fast backtrace support how to parse the dwarf expressions. Then the cache was too small. We were calling backtrace for so many different places that previously had all hit the backtrace cache and not the full unwind cache. We now had to go and make the full unwind cache quite a bit bigger to make sure that we could actually hit it all in the right places. So even if the backtrace cache failed, we would hit the normal cache. So now in libunwind, the cache size is configurable. And then we still hit the global lock contention in deal iterate PHDR, which is really what was slowing everything down. So we were hitting global contention for a multi-threaded program. I don't actually have a great solution for that yet. You can, of course, do things like lock-free lists, but nothing is guaranteed to still be safe with DL close at the same time. So here's some benchmarks of the various different unwinding libraries. For this, I just set up a giant stack of call frames. So I think I used 100, and then called backtrace. So if you call backtrace normally in GCC, you'll get libgcc running through the full exception handler framework. I also compared it to a simple frame pointer unwinder, which is of course super fast, assuming you've compiled with frame pointers. And then I compared it with unwind backtrace, which is using our fast backtrace cache to see how fast it goes, which of course is quite a bit faster, in order of magnitude faster than libgcc. Now the other two, how I ran them was actually pretty cool. Because we're using a consistent ABI, the Itanium ABI, I didn't actually have to recompile the program at all. I just did LD preload in the exception handler for libunwind and LLVM's libunwind and just reran the program. So it was super easy to get these other numbers as well. You can actually change your unwind library when you're about to run your program using the linker. So here's libunwind. It is a little bit slower than libgcc, but not too much. And LLVM's libunwind is much slower. It looked like when I was trying to profile a little bit that the parsing of the dwarf was taking longer, although I'm not 100% sure why. I am sure why libunwind is so much slower. It actually provides a guarantee that the rest of them don't provide. By default, it is signal safe. So if you want to do backtraces or do some stack unwinding from a signal handler, libunwind lets you do that. Signal safety encompasses also memory safety as well. So if you're writing an allocator like jemalloc or tcmalloc and you want to take a backtrace, you pretty much have to use libunwind or some sort of custom frame pointer unwinder, because otherwise you're going to get a recursive call back into your allocator if your unwinder is trying to allocate memory. And why would it allocate memory? Well, for its cache. It probably wants to allocate some memory to stick something in its cache. So both jemalloc and tcmalloc have the option of being compiled with libunwind to give you nice backtraces. As it turns out, we could turn off the signal safety and see how things look. So I just configured it, disabling all the signal safety. There's various ways to do it. I just put one of them on the slide. And indeed, the caching, both the fast backtrace support, because it has to go all the way down, gets a little bit faster. And libunwind gets a little bit faster itself if you're just using the normal dwarf cache as well. So caching at a higher level is definitely faster than caching lower level and rerunning all the dwarf expressions all the time. Cool, so that's just about all I've got. I hope you've learned a little bit about exception handling. So the root of what we're trying to do with exceptions is split the function into two, at a hot path and a cold path. We can speed up the cold path by using a lot of caching, but we're not talking about like an L1, L2, L3 cache. It's probably just in memory somewhere. And how much are we caching? Totally depends on your unwinder. For libunwind, even if you're using a very large cache, it's probably less than a megabyte of memory. For our production programs that we use at Facebook, it's still quite a small amount of data. So if you miss cache, you're going to have to go all the way down to the operating system and ask it to iterate over all of your different loaded libraries and take a global lock to do that. So it's going to be significantly slower. Cool, thanks. Anyone have any questions about unwinding?
Thanks for the talk. I'm afraid I know more about exceptions than I want to. This is complex. Can you tell us something about the past security vulnerabilities related to unwinding and the mitigations that were put in place after those?
No, I'll refer you to the research paper. I don't know a lot about the security implications. Sorry.
Thanks.
Let's say there are two shared objects which define the same exception class. And they are opened using delopen, so that linker doesn't get a chance to use one of them. But they are both present in a process.
Okay.
How does catch statement understand which exception is which, or either?
So you're asking if you deal open two different libraries and there's two different objects that are going to be thrown, but you're asking if they're different or the same and how
Yes.
they're different. So for this is taken care of at the language level, as far as I know. That the C++ will give them different type IDs that they're compared. So either they're the same or they're not. They're different type IDs in that comparison.
So it uses RTTI.
Yes. So exceptions definitely use RTTI when doing the comparison. So depending on which compiler you're using, even if you turn off RTTI, but you are using exceptions, you'll still get some of the RTTI machinery.
Thanks.
I know you talked more about the sort of catching side, the unwinding side, than the throwing side. You mentioned CXA allocate exception and that there's the heap allocation involved in exception handling. Is there any even experimental investigation into how do we get rid of that heap allocation, or how do we customize that heap allocation?
Not that I know of, no.
Hi, so I'm used to dwarf meaning debug information, which can be safely stripped from the executable. This should be a simple question. The dwarf in the exception handler, that's just using the same format, but presumably that's pretty critical to the execution and can't be stripped. Is that correct?
You are correct. So while debug information is in a different section. It's not in the EH frame section. It's in its own debug section. So if you want to split the debug info, it can be in a different file, but the EH frame section is always in the same. And while they both use dwarf, the information is completely separate. You can actually pull enough information from the debug info to do unwinding, but not vice versa. And so it's basically a stripped down debug section that always ships with your binary.
Okay, thank you.
Hi, great talk, thank you. Unwind information, is it available for every instruction in the function, or only for call sites and throw exception?
That is an excellent question. It used to be, 10 or 15 years ago, only available for throw statements and call sites, which, as you would expect, those are the only ones we actually need to throw exceptions. This is not the case if you want to do backtrace. You can backtrace from anywhere. You can set up a signal handler and then send it a signal from anywhere, and you want to do backtrace. So as far as I know, for the last 10 years, all the compilers have been generating it for every instruction in functions.
So in theory, if I want to turn access violation into a proper C++ exception, it should be possible, right?
Yes. So libunwind allows you, it is signal safe. The C++ exception handling machinery that I've seen in libstud C++ is not signal safe. So in theory, yes, you can do that. I haven't seen anyone do it yet.
Thank you.
In one of your early slides, it looked like that you were catching the exception without a const reference. So I'm curious how that can affect unwinding performance.
I don't know the answer to that, sorry. Most of my experience is with the Itanium language agnostic piece of it, so probably asking a compiler writer would be better.
Thank you.
You mentioned a potential issue with multiple threads loading and closing libraries. Does that really happen in production? Because I don't see the use case of multiple threads just going by opening and closing library all the time.
No, it generally doesn't happen in production. I have never seen it happen in practice, but it's the reason given for having to always take the global lock. And I've totally written a small, unit test that can exploit it, but I haven't seen it happen in production.
As for the previous question, I'm pretty sure I read that catching by reference or by value is exactly the same, but I wouldn't be quoted on that. Just double check.
I would be interested in getting under control the worst case execution time, which is involved in exception handling. There's certainly the memory allocation, which sort of brings us a kind of unbounded, theoretically at least, factor. Is there any other?
So when I've seen the worst case in production, it has all been lock contention on the global lock.
Right.
If you are a single-threaded program, the worst case I've always seen has been parsing the dwarf instructions themselves, grabbing them off of disk and then parsing the format, which you need a full parser to parse it, and then actually executing all the instructions and finding the correct registers to restore. So this all kind of dominates any sort of allocations.
This global loader lock smells a lot like the loader lock from James McNellis's talk about DLLs the other day. And of course that was about Windows DLLs, not POSIX. But is this exactly the same idea? And in his talk, he pointed out that there were ways you could deadlock yourself by, DL opening things inside DL open, or Windows equivalent of that.
I didn't see that talk, but
with
it
exception
sounds
handling?
almost the same. And yes, I am sure you could deadlock yourself by DL opening and DL closing things from different libraries.
What if you did it within a destructor? Would that be a problem if you stack unwound through that destructor, or is that not a problem?
If you are unwinding and you did it within a destructor and closed the library that you're unwinding through, yeah, that could be a problem.
Okay.
In an answer to your previous question, you said that typically it doesn't happen that someone DL opens and DL closes in different threads. So, is there a way to compile libunwind or LLVM unwind to assume that no one does that to get the benefit of not having to use the logs? And that's on your fault if you broke the assumption?
There's no way to do that currently that I know of, but it is high on the list of things that I want to fix.
Yeah, okay, thanks.
Thank you.